Today we're going to watch a video of a crumpled piece of paper as it drops to the floor. We'll extract motion data from the video, construct models using Newton's second law, and compare the predictions of the models with the observations. Much of what we talk about will seem familiar from our past work because we're using the same fundamental principles and key tools and techniques to understand and to predict motion. First, let's discuss extracting the motion data from the video of the crumpled paper. We are using the same procedures we discussed in detail earlier when we examined the motion of the soccer ball. Those steps can be reviewed by looking back at that video, so we won't repeat those steps here. We encourage you to try analyzing the motion of the paper on your own. You can do that with Tracker and the sample video, which you can download using the link which should pop up now. Here's the summary from my analysis. The video was recorded at 30 frames per second, and the height of the student shown, 1.88 meters, was used to calibrate the length scales in the video. The coordinate system was chosen with the origin at the center of the paper, just before it was dropped. The y-axis was aligned such that the object moved in the -y direction as it fell. Note that because the camera was tilted when the video was made, we need to tilt the coordinate system slightly to align the y-axis with the direction of motion. We marked the center of mass for the object by I in each frame. In many frames, the object was blurred, and we marked the center of the blur as our best estimate for the center of mass, the average position of the object. From the analysis, we obtained the observed position of the object as a function of time, shown in blue squares in a plot that we generated using a spreadsheet. We see that the motion of the falling object is observed for a total duration of 0.7 seconds, and we emphasize that at the beginning of the video, where we start our analysis, the object is located at the origin, by virtue of our choice of coordinate system, and the object is at rest. It's moving with zero velocity. As we know, we will need to use this information to set our initial conditions for our model. We now turn to applying Newton's second law to construct computer models to help understand and predict the observed motion. We have a case where the velocity is changing, meaning the change in the velocity is non-zero. So as we discussed, this suggests we have F net is non-zero. So there's at least one agent in the surroundings that's exerting an influence on the object. We suggested earlier that the Earth exerts a force, the weight force, on the object. So let's start with a model that includes the weight force as the only force, and therefore the weight force is the net force acting on our object. And let's see whether the model we build with that assumption can predict the observed motion. We'll start by launching vidle, and from within vidle, we'll open the Python program lab2start.py. As always, we encourage you to go through these computer modeling steps on your own. To help you get off to a quick start, you can obtain this Python program and supporting files using the link which should pop up now. Let's run the program. If you do so and you see something like this, then the program is ready for us to put in the correct physics. So let's get right to it. First, by putting in the correct initial conditions and system properties. With many of the lines of code we will now show, we will already have made the necessary changes. As we point those out, you can make the same changes if you're following along with your own code. So right off the bat, we know we need to specify the mass of the crumpled paper, which we measured to be 2.93 grams using a good scale. So as usual, we convert all units to SI because we're using SI units here. We also need to specify the initial position and initial velocity that we estimate from our analysis of the video. As we already said, the initial velocity is 0 since the object is dropped from rest, and with our choice of coordinate system, the object starts at the origin. We also choose to start measuring time at t = 0 seconds at the start of our observation. We have some additional initialization to look at. We need to check our time step delta t to make sure it's small compared to the 0.7 second duration of the observation. Here we see it set at 0.001 seconds, so that seems reasonable. We also need to provide some initialization for the interactions we're modeling. In our model for the weight, we need to specify the constant g to describe the magnitude of the weight force. And we also need to define here the axis unit vector, j hat, that we will use to specify the direction of the weight force. Now let's look at the loop, where we do the actual motion prediction using Newton's second law repeatedly. We've already put in the correct code here for predicting new velocities using Newton's second law, and for using the velocity predictions to update the predicted positions. We also have set the total time we're making predictions to be consistent with the total observation time of the analyzed motion in the video. Up to this point, all of these steps are basically the same procedures we applied earlier with our models in constant velocity motion. Now we come to the chief difference. We need to specify the non-zero net force of the surroundings on our system, the falling object. We said we're going to assume that the net force is just due to the Earth's gravitational pull, the weight. We need to translate the algebraic expression for the weight force into computer code here. What would that weight force look like in code here? Here's one way to write this, where we made sure that we write the vector weight force as a vector, and we remember to use the correct syntax. For example, we defined the variable ball.m and set that equal to the mass of the crumpled paper. So we need to be consistent and use that same variable for the paper's mass when we write the code for the weight force. Notice here too, the weight force is the only force that contributes to the net force. That's all the physics, so we're ready to run our model. Here's what it looks like. The visualization seems roughly correct, and the plot of the position versus time also looks reasonable. Let's compare the model predictions more carefully by plotting them on the same graph as the observations. The model output will show up in the file pythontest.csv in the same directory where you have your computer program. As we discussed earlier, you can use your favorite spreadsheet program to construct the plot, and you should get something that looks like this, where we show the predicted position versus time by the black line. We see that for time t small, the predictions do a reasonable job, but for t larger, our model predicts the object to fall farther than what we observe. This suggests that the object's motion is affected by an additional interaction with the surroundings. Earlier, we discussed the possibility that the air could exert a force, an air resistance, or as we'll call it, a drag force. So let's see what happens when we put that into our model as well. Notice that in this discussion, we are in evaluation mode. We've examined how our model and our observations compare, and from that examination, we've reconsidered our original model assumptions and decided to try to improve our model by adding one more interaction, the drag force on the system. To do this, we don't need to start from scratch with our model. Everything we put in earlier, the initial conditions, Newton's second law, the interaction of the Earth with the object expressed as the weight force, all that is still part of our improved model. We need to make only one major change, add in the drag force. Here's one reasonable way, expressed in algebraic form, that we discussed earlier to model the drag force. We need to convert this to computer code and insert that in here. See if you can do that correctly now. Here's one way to write correctly the line of code for the drag force. And notice that we have also included the drag force in the computation for Fnet, which is, as always, the sum of all the significant interactions with the surroundings. There is one loose end here, however. We haven't said what the constant b, the proportionality constant, is. We said earlier that b might depend on the details of the airflow around the object, which, in turn, could depend on the properties of the object. For example, the object's shape and size. Instead of going into the details on this, we will take an empirical approach and use our observations to help us find a good value for b. The observation we'll focus on for this is the final observed position. This print statement, which is the first line after the loop in our code, prints out the predicted final position in the output window. So in our code, we will try different values of b each time running the code and then looking at the output window until we see the predicted final position is close to the observed final position. From this procedure, we obtain this value of b, which has the units of Newton seconds per meter. Roughly speaking, we're performing a fit to our drag force model using some knowledge of our observed data. There are other reasonable ways to do this. Here, we just made one choice of a reasonable way. We're ready now to compare the predictions of this revised model with our observations. But first, we're going to take a little detour and discuss how to add one more feature to our code to help us visualize what the model is predicting. In the real world, we are typically unable to see forces, but in our computer model, we can use arrows in the display window to represent the vector forces. By watching how the arrows change in the display window as the visualized object moves, we can get some insight into how the forces on the object behave in our real-world observations. To put arrows into the visualization, we first need to create the arrows. The lines of code that do this for 2 arrows are already in place. The color of the arrows is set here. Now inside the loop, just after the code that specifies the quantities that we are graphing, we need to specify the lines of code that tell the computer how to draw the arrows. 1 to represent the weight force, and 1 to represent the drag force. As always, when drawing arrows to represent vectors, we have to make some decisions. First, we need to decide where to start drawing the arrows, that is, where to place the tails of the arrows. This is set by the attributes arrow1.pause and arrow2.pause. A natural choice is to put the tails on the falling object that is being pushed and pulled by the forces. Next, we need to decide how long and in what direction to draw the arrows. That's specified by the attributes arrow1.axis and arrow2.axis. The forces themselves contain the direction and magnitude information, so you might think that all we need to do is simply set these attributes equal to the predicted forces, say something like this. That's not quite right. You'll recall that an arrow's length only represents the magnitude of the force. This is because the arrow's length is really a length, but the magnitude of the corresponding force has different units and dimensions. So we need to make an extra decision about how long to draw an arrow for a given magnitude of force. Let's work out how to make that decision for the weight. For our crumpled paper, the magnitude of the weight is approximately 0.03 newtons. We need to decide how long to draw the arrow to represent this magnitude. Our visualization window represents a field of view that is a few meters on each side. So, in order that we can easily view the arrow representing the weight, let's choose to draw an arrow that's 2 meters long to represent the weight. To do this, we will set the length of the arrow to be equal to the magnitude of the weight force multiplied by an appropriate scale factor we'll call arrow scale. In this case, the value of arrow scale we will choose to be 2 meters per 0.03 newtons, or approximately 70 meters per newton. Now that means we can set the attribute arrow1.axis, which tells us how to draw the arrow to represent the weight force, to the weight vector times this scale factor, and that will give us an arrow that both has the length we designed and points in the direction of the weight. This is a little involved, but it's necessary as we have to be very specific like this when we tell the computer to draw an arrow to represent a vector quantity like a force. we'll use the same arrow scale to draw the arrow to represent the drag force. And so here's how we specify the length and direction of arrow 2, which represents the drag. Now let's run our revised computer model. Here's what we see. First, as we watch the object fall in the display window, we see the yellow arrow representing the weight force is down in the -y direction and not changing in direction and magnitude. That seems sensible. The blue arrow, representing the drag force, is not visible at first, but then the arrow appears, pointed opposite to the direction of motion, upward in the +y direction, and getting longer as time advances. This makes sense too. The magnitude of the drag force in our model depends on the object's speed. At first, the object is moving slowly, so the drag force has negligible magnitude for early times. But as the object continues to speed up, the magnitude of the drag force becomes more significant. The graph shows the predicted position versus time, which looks roughly right. To really compare this, we need to plot this in our spreadsheet, like this. So we can compare the prediction of our model with drag and weight to our observations. Let's emphasize here at the very beginning of this graph, the model doesn't really predict. We used this part of the observations to set the initial conditions for our model. Also, now at the end of the graph, we don't have a prediction either. We fit the constant b in our drag force by demanding that our model produce the same final predicted position as the final observed position. Now in between, we do have model predictions of the motion, which on the whole seem okay, but they're still not perfect. In particular, the model seems to underpredict the motion during the in-between times. Why is that? Let's do another round of evaluation. Let's first look back at our observations captured on video. If we look at the video, we see that there is some distortion. Notice the doors, which we know are rectangular, don't look rectangular. This is an example of perspective distortion, which indicates the camera was viewing the motion at an angle. It might be a good idea to repeat this experiment, keeping in mind what we said earlier, that it's always best to try to view the object's motion straight on, meaning the viewing direction should, to the extent possible, be perpendicular to the plane in which the object moves. On the modeling side, there's something to wonder about too. Maybe we could still do better with improving our model. For example, one common alternative for modeling drag is to use a model where the magnitude of the drag is proportional to the square of the speed. Would that produce better results? You'll have a chance to explore this issue for yourself as part of the second lab on falling objects that you will perform on your own in your own surroundings.